let's start recording and get started with class, with the second to last lecture. You guys are so close to never seeing me again. Right, so let's see. In terms of announcements, your homework is due in 5-ish hours. So I'm sure that's irrelevant because all of you guys have finished. And if you haven't, then you got like roughly 1 hour per problem, which should be more than enough time. I mean, I did it in like a few minutes. Right, so other than that, then you have the final exam, which is on, what, I think a week from Friday, is that right? The 19th, apparently? Whatever's on the course calendar on that Google Sheet. And then you're out of here. In terms of practice material, I would suggest like the midterm is a pretty good sample of like the kinds of problems that we tend to write on these things. I can also try to dig up some old exams from like the last time I taught with this textbook at least, so the circumstances were very different. What was that? We do have to write that exam. But the good news is we have like a week and a half to write it because it's like the very last exam, which is frustrating for those of us that would like to be done with this semester. Right, so any logistical questions, comments, concerns? I think it's pretty straightforward. Fantastic. So today and in our next lecture, we wrap up our treatment of numerical methods by considering differential equations. So roughly our plan for today, we got about halfway through the story last time of at least the basics. Today we're going to go over some more advanced methods for integrating ODEs. And then next time, we'll have a choose your own adventure. Maybe like when we get closer to the end of class, we can have a quick vote among the 4 students who are here. We can use our TA as a tiebreaker about whether the next lecture should be some advanced stuff in machine learning that makes use of some of the techniques that we're talking about here, or we can have some exam review. Either way, so I'll let you contemplate that for now. Right, so that's where we're at. Any technical questions from our discussion so far? So to give a quick review of the previous lecture, essentially, remember we started by solving very generic versions of differential equation, but we did reduction after reduction after reduction, and eventually we decided that it was okay to just solve things that were of the form y prime equals f of y. And of course, when I say that, that isn't to say that the best possible algorithm for solving some things that were in some of those more generic forms is derived through such a reduction, but it's to say that such a reduction means that if an algorithm applies for this one, then it also applies to those other ODE. You guys understand the difference? Like there may be some really awesome algorithm specifically for second order ODE, but we can also use this thing to solve second order ODE. Okay, and so essentially when you think about algorithms for integrating ordinary differential equations, in my mind at least, there's sort of an interplay between 3 different things. And like I think it's easy to lose the forest through the trees in this discussion. And in fact, there are entire textbooks which are just long lists of different ODE integrators. In fact, there's like inductive procedures you can make to make infinitely many of them. You can just do this all day. But essentially, there's sort of a trade-off that happens. There's really some kind of Pareto frontier between 3 different things. One of them is accuracy, right? So like, you know, as my time step goes to 0, at what rate does my approximation of the solution to the ODE approach the true solution? There's stability, which is for a fixed, like, positive time step h, does my thing explode if I run it long enough, or is it stable? Does it dissipate energy? Does it add energy? And then the third thing is efficiency, right? That like every step of my ODE integrator might take a ton of computational time, like if I have to solve an implicit system. And so essentially, there's like some kind of annoying curve that relates all 3 of these things, at least abstractly speaking, which is why we don't just all, it's not the case that like I come to class on ODE, I reduce it to this, I give you 1 integrator and we're done, right? That would be like a really nice story, but sadly that's just not the case here. The reality is that there's a bunch of different options and they all trade off between these things and they depend on the details of your problem. It's very frustrating that way. Yep. And so in particular, in our previous lecture, we kind of already explored that difference just a tiny bit with 2 of the most classic numerical integrators. And these are forward and backward Euler. If you call it Euler, you fail your exam. And essentially, forward Euler kind of does what you would expect, right? It just takes y prime, multiplies it by an h, and adds a little increment. This is called an explicit method, meaning that like yk plus 1 is on the left-hand side, yk is on the right-hand side. So this is just a formula that I have to evaluate. And it has h squared truncation error locally and globally order h. Remember, those are off by a factor of 1 over h because you account for the fact that you need more time steps to get to a given fixed time. Right? The challenge we saw with forward Euler was that if we took a time step that was too big, it would spiral out of control. Right? In fact, the mythology is usually that forward Euler tends to have the property that it adds energy to physical systems. A little bit of that's mythology, because obviously it depends on the specifics of the equation you're solving. But like I think generically speaking, that's usually true. On the other hand, we have backward Euler, which is an implicit algorithm, meaning that yk plus 1 appears in two places. Hopefully you guys see, this is a system of equations I have to solve. Like we can do it in closed form when it's a linear ODE, but usually you need to use like a root finding method to actually solve this thing. But in exchange for that, even though we have the same order accuracy, if we look at our kind of three axes here, the stability was much better, right? At least for the linear ODE, it was unconditionally stable. Yeah? And what about the efficiency? Way worse, right? Because now I have to solve something instead of just typing into a formula. Does everybody understand the story so far? So just to extend our story ever so slightly, we can talk about, I think for the most part, when we talk about the model equation, we thought of y as a scalar. But of course, we can solve a slightly more general ODE, which is y prime equals some matrix A times y, where y of t is in a generic Rn, right? And the closed form solution to this is equals e to the a t times y of 0. Where here, this notation e to the at, I don't know if you guys are familiar, it's called the matrix exponential. And essentially, it's like exponentiating all the eigenvalues is really what's going on. Is this familiar? I see some nods. And Chris is wildly typing on his laptop. OK? And then essentially, we can derive formulas for forward and backward Euler. So for example, here they are on the screen. Obviously, for forward Euler, what do? I take y, and I just add h times y prime. Right? So if I factor that out, I get I identity plus h times a. And for a time step of backward Euler, it's almost the same. But now I have a matrix problem I have to solve. OK? So in any event, I think the only reason to write this here is I think for a single-valued ODE, it's not obvious the third aspect, which is efficiency. But given all the things we've done in this class, now it's pretty clear, right? Because like, you know, the first one is just a matrix multiply. The second one is solving a linear system of equation. And if we hopefully recall from the first like 8 weeks of this class, the second one takes a lot more time on the computer. Yeah. Cool. So these are two examples of solvers. But notice that like there's still some axes that we haven't really explored here. In particular, both of these things have had the same order of accuracy, right? And so you might wonder, like, can we do a little better than that? And the answer, of course, is yes, because that's why I'm here. OK. So in particular, you know, one of the kind of interesting things is that we'll see a lot that, you know, this course is structured correctly in the sense that we first covered numerical integration and differentiation, and now we're doing ODE. And essentially, for every trick there, there's an ODE integrator that looks more or less the same. Like this is just the way that it goes. So for example, in forward and backward Euler, like how do we construct it? Do you remember this? Like we essentially use the divided difference approximation of a derivative, right? And that's what gave us that order h accuracy for our integrator. Now, we remember from the numerical differentiation lecture, I hope, because you have a final coming up, how could I make that a little more accurate, like a numerical derivative? Yeah, I could use the center difference, right? And in particular, here's kind of a sneaky thing I could do. So here we're going to like use a bit of an abuse of notation here. We're going to introduce a fictional quantity for a second, which is yk plus 1/2, which is like what would be the value of y at the time between yk and yk plus 1. We're going to eliminate it in a minute, but like in principle, like we could compute such a thing if we wanted to. And why would we do that? Well, the center difference formula tells us the following. It says, well, I could get yk plus 1 is equal to yk plus h. And now, if I evaluate it at k plus 1/2, let's say that I had such a quantity, right? Then now the happy news for us is that the order error isn't h squared anymore, it's h cubed. Remember that this is cubed instead of squared because I kind of multiplied both sides by h when I made my integrator here. So great, this is exciting. There's only one problem, which is now I've got 3 y's, and 2 of them are unknown. So I can't, this is underdetermined. I can't actually use this as an integrator. Right? So, what am I to do? Well, we might recall a second thing. This is fun. We're like applying all the math from the last couple lectures and deriving these things. Now, when we derived the trapezoidal integrator, we also actually proved a different fact in the same lecture. We showed the following, that f of yk plus 1/2, well, we can get it by taking the average. So we can say this is f of yk plus 1 minus, plus. F of yk divided by 2 plus order h squared. You might not remember this from the lecture we had on trapezoidal method, but it basically came from a Taylor series argument. Like we expanded a Taylor series about this midpoint, and then this is the order error that we got. Yes, Axel? Trapezoid rule was bad or not necessarily bad, but like it turned out to have the same order accuracy as midpoint. But here we're solving different problems. It's not the accuracy that's the problem. It's more that this is just not a computable object. so you're right. Like the argument is making use of a formula we proved, but the drawbacks of trapezoid might still apply here. Yeah. Okay. So why would I want to do that? So I've got this little formula here. So I can plug that in for f of yk plus 1/2. Notice in this expression here, it's multiplied by h, right? So this big O of h squared becomes h cubed. This is going to become important when we talk about Newmark integrators, if we get there today. Okay, so in particular, this is equal to yk plus h times f of yk plus 1 plus f of yk over 2 plus big O of h cubed. Okay? So, by the way, like we can derive all these integrators. Like I think you guys are starting to see the pattern, right? Like I write some Taylor series expression, and then I just slice out the higher order term, and like, ta-da, here's my integrator. And notice that like that's exactly what we can do here, right? That in effect now we have an integrator. Notice that it is implicit because of this guy, right? There's now a yk plus 1 on both sides, but it's averaged with yk, whereas in backward Euler there's just a yk plus 1, right? In exchange for that, you actually get a higher degree of accuracy. And so this, I see ya, is called the trapezoid method. It's implicit, right there it is on the screen, with cubic localized error and quadratic global error. So we call this second order accurate. Yes? Sure, yeah. So if we have an expression like what's on the screen here, right, what is our goal? We have the state of our system at time k, and our goal is to predict it at time k plus 1. Notice in this expression, yk plus 1, which is our unknown, is on both sides, right? So in order to actually find yk plus 1, I have to solve this equation. So we call this implicit. An explicit one would be like yk plus 1 equals some formula in terms of yk. Explicit means there's a formula. Yeah, that's right. Okay, so this is trapezoid method. What do you think our next analysis is going to be? So we know it's accuracy. We know it's efficiency, kind of. It's implicit. Stability. That's absolutely right. I think in the interest of not inducing total boredom for you guys, we might, I mean, it's the same calculation over and over again that we're doing here, so I'm happy to have a bit of a spoiler alert. Unless you want, I'm happy to walk you through the stability of trapezoid method. Okay. So here's an example, by the way. So for y prime equals ay, this is the integrator you get. Kind of funny looking. Notice it looks kind of like a half, if you kind of squint at it, it looks like a half step of forward Euler followed by a half step of backward Euler. This is kind of what's going on. one kind of weird question you might ask, like, I mean, this thing kind of looks symmetric in yk and yk plus 1, but if you read this expression, it kind of feels like, you know, you do the forward and then the backward. Here's a question that I'll let you ponder at home. At least if A is symmetric, does it matter what order you do these two steps in? Which is a fun thing to think about for me. Okay, so, right, so in any event, I think we can probably skip the stability calculation for this thing. If you're curious, here it is on the screen. It's a bit ugly to derive. It's just arithmetic, but it's ugly. So this is what it looks like for the model equation. And actually what you will find is that trapezoidal method is unconditionally stable. There's never a situation like forward Euler where it can spiral out of control. So trapezoid method, like, oh my God, we should start getting excited, right? This is implicit like backward Euler. It has higher order accuracy than backward Euler. And it has higher, like roughly the same efficiency. And the third thing, I just repeated myself 3 times. Accuracy, stability, and it's also unconditionally stable, right? So the question is there ever a case I should use backward Euler? Right, because like somehow like they feel very similar, but this one's more accurate, right? Like they're both implicit, they both, you know, have like roughly the same stability here. And the answer is actually a little subtle. I mean, like from the perspective of the story that we've laid out so far, the answer would be kind of no, right? Like this is more accurate and the same computational cost. Like fantastic, let's use it. But it turns out qualitatively, these numerical integrators still behave quite differently. And actually qualitatively, a trapezoid can have some really funny behavior. So let's say that I'm solving y prime equals ay here. And I take a time step, like an h. So for one, remember that like a being negative is the stable version of this problem. Like that's the one that's in exponential decay. And remember, what did it look like for backward Euler? Like if I took too big of a step in backward Euler, it just kind of like zip to 0 quickly. What happens with the big step of this expression? Let's kind of stare at it for a second. So in the numerator, so remember a rather is negative, right? So h times a is negative. So what is the numerator? It's going to be a negative number, right? What about the denominator? This is 1 minus ha, but ha is a negative number, so it's always positive, no matter how big h is. So for a really big h, this ratio is going to be some negative number. So qualitatively, this is what can happen. You actually get oscillatory behavior. So it's really funny. So here's the behavior of trapezoidal integration. So you can see like the big chunky lines are the ones where you take really big time steps. And it's still stable. Remember, stability just means that you don't spiral out of control. And it never does. You can show that like you can take a gigantic time step. And the worst case is, yeah, you'll oscillate up and down, but the oscillations will slowly decay to 0. So this is sort of the difference. Essentially, one thing that we haven't added here is long-term behavior. Right? Like we haven't really talked about like what do these things look like when I take a really big h, right? The accuracy we've talked about is as h goes to 0. And a more advanced question might be, like if I take a really big h, does it at least qualitatively kind of preserve properties of the system that I want? And you could argue that for trapezoid, it really doesn't, right? Like it starts to look like a sine wave, which is not what you might want. Yes? Mm-hmm. Mm. Yep. I think in calculus you're also interested in the intermediate behavior, right? Like all of these things are designed to like predict how dynamical systems behave, right? So that's a function of time. Maybe you're confusing integrator like quadrature versus integrator for ODE. Possibly. I do think in calculus, oftentimes they just give you a long list of these different ODE integrators and you don't know the difference between them. Now we're going through this in a lot more detail. Yeah. Cool. And the good news is all of these things agree for like really small h. So like in some sense, like if you've got a lot of time on your hands, it doesn't matter. Okay. So right. So essentially, I think like at this point, okay, like we've done a billion examples. I think you get the point. That like, you know, convergence as h goes to the story isn't the whole story. Neither is stability. You know, oftentimes we also have to think about what happens as h is some fixed positive number. And that's like more of a qualitative story, right? Because that's really a byproduct of how you've discretized your problem, right? Like it has nothing to do with the smooth physics. And so like this is where one of these cases where actually just looking at the solution might give you a bit of a clue that like something is up. So in your homework, you have another example of that, right? So in backward Euler, right, everything kind of decays to 0, right? So like if I'm simulating like a person on a swing, slowly the swing will like grind to a halt and stop, right? Like a pendulum. What you're proving on your homework is that if for this very carefully designed integrator that's on your homework, that doesn't happen. That like energy is kind of conserved over time, so the swing will just kind of happily keep going. In fact, if you haven't coded it, you should. Okay. Any questions so far? Cool. So, guess what we're going to do? We're going to derive more integrators. This is a lecture on numerical ODE, and there's a billion of these things. You should be glad you're not taking a class on this stuff. Okay, so there's like so many different ways to derive these. I think for the most part, the arguments we've made so far look like Taylor series arguments. Like we've kind of like munched together Taylor series the right way, and then, you know, like ta-da, we have another integrator. Beyond that, you can also do a slightly different thing, which is you can instead work kind of backward from quadrature rules instead. And that actually leads to an entire class of integrators that are extremely popular and well known. I think the best one that's known is RK4. If you've played in a video game, you've used most physical software, you've downloaded MATLAB and used the ODE integrator, whatever, that's probably implementing RK4 by default. So it's worth knowing where that comes from. Okay, here's the basic, extremely deep observation I have. So let's say that I really do have y as a function of time, right? Then notice what I've written on the screen is basically tautology, right? Like it's just saying I get y at the next time by integrating y prime, but y prime is f of y by definition of our ODE here, right? So that's all this is saying. Everybody agree with this expression? There's an important name for this formula. Does anyone remember this one? It's fundamental. Fundamental theorem calculus. That's absolutely right. That's all this is. Slightly reshaped by putting yk on the right-hand side, I suppose. Okay. So the first thing that we can do, just for yucks, is actually derive this same algorithm, but instead of doing that using a Taylor series argument, we can instead do it with a quadrature one. So I think that's worthwhile. Well, I don't know if it's worthwhile or not, but we're going to do it just to give a small example of a larger pattern, which is as follows. Like essentially, we can jump right to the last step of this thing because we already know the error of trapezoid method, right? In particular, right, so we know yk plus integral tk to tk plus 1. I'm already dreading deriving these Newmark methods, which have like a billion of these integrals, and it's going to get really ugly. Maybe we'll do that next time instead. dt. Right? And one thing we can do is plug in any of our favorite quadrature formulas for this integral, right? And remember that like this integral is exactly equal to, or up to a fudge factor. It's equal to yk plus, well, what do we have to do? Remember how the midpoint integral works, for example? So I do h over 2 times f of tk plus 1 plus f of tk. Sorry, this isn't the midpoint. This is trapezoid rule. Like that. Okay, sorry. I underlined it because I was about to write divided by 2, but I guess it's already there. and just by virtue of knowing the error expansion for the trapezoid rule, we already have that it's order h cubed. So like our argument above was a little bit redundant. Like we like basically two lectures ago we proved exactly this formula, right? So had we started with the fundamental theorem of calculus instead of with the Taylor series, we could have skipped a step, right? Does that make sense? Now here's a question. So the good news, like we kind of like trapezoid integration because it has this higher order accuracy. Right, so like if I have some system that's really unstable and I have to take tiny time steps anyway and do implicit stuff, and they're small enough that maybe that oscillatory behavior isn't a problem, then like this is a good integrator to use, absolutely. But there's a different question you could ask. We could get greedy. You could say like, fantastic, well, I love this higher accuracy, that's cool, love that. But the only higher order accuracy integrator we know so far is implicit. The question is, can we make it explicit? What do we think? Probably yes. Yeah, this is a whole lecture here. The next question, how do we do it? Yeah. Approximate the thing with the other thing. Thanks, Harry. Appreciate it. I always I like the positive attitude and constructive comments. So, right. So let's do exactly what our colleague from the math department suggests and approximate the thing with the other stuff. In particular, we're going to do something kind of funky, I think, which is the following. So notice we have this term is basically the one that's causing us all our headache, right? So let's everybody repeat after Harry. We approximate the thing with the other stuff. Right. So we have f of t. Oh, sorry. That should be yk. You gotta stop me when I write stupid stuff. Good news is my handwriting is so bad that it looks like a y anyway. Okay. So right. So like that. And now we're going to derive a new set of integrators. These are called RK integrators, which do a really funny thing. Here's yk plus 1, and we don't have yk plus 1, right? Like this is the object we're trying to find. Here's kind of a funny observation. Notice that it's multiplied by h. Right? It's multiplied by a small number. So I can actually get away with kind of a crappy approximation of yk plus 1, and it might be okay because it's scaled by something small. And so we're going to do something that feels the tiniest bit tautological, but it's not tautological, which is the following. What is yk plus 1? Well, one thing that I could do is get yk plus 1 with the forward Euler method. In particular, I'm going to write a true statement, but we're going to compile it because it feels weird. This is equal to yk, right, plus h times f of yk, like that, plus O of h squared. And then all of that goes inside of f. Do you guys see that this is a true statement? Like, all I did was substitute in a different expression for yk plus 1, but it is a true expression so long as I have that O there. Yeah? Any questions so far? So what should I do? Harry, what should I do? I should approximate the thing with the other stuff, right? So what was that? Yeah, I'm going to do Taylor expansion, but I'm going to do it in f, right? And if I do the Taylor expansion of f about this thing, right, then what it's going to equal to? It's going to equal f of this first argument plus df times something in the difference, but the difference is already order h squared. Do you see that? So in particular, this thing is equal to f of yk plus h times f of yk plus order h squared. So in other words, all I did was kind of move that out there. So what did I just show? I showed, so like there's essentially three objects here. I can evaluate f at yk. So like let's think about our ODE, right? So we've got these flows. They look like exponentials, right? The first thing I did was I evaluated f here, right? Now in an ideal universe, I would follow this curve down and I'd evaluate f like that, but that's expensive. So what I did instead is I linearized and evaluated f here instead. and the point is that that's like kind of close enough. These two numbers are close to each other. Yes? Yeah, you can think of this as sort of one iteration of Newton's method applied to the root finding problem of doing of solving this implicit system. Yep. This is good observation. So, and in fact, actually, you can derive a lot of things. There's a really funny situation when you do these implicit integrators. You have a system of equations to solve, right? So now you go back to our Newton's method lecture and you plug that in here. But like think about it. If I do Newton's method for 3 iterations, say, but I always do it for exactly 3 iterations, what I've really derived is an explicit integrator. Do you see that? Which is take yk, do 3 Newton iterations, and then stop. And in fact, you can derive a bunch of integrators that way. There are a bunch of different ways to do this. Good observation. OK. So what have we shown? We've shown that we can get f at yk plus 1 by doing a crappier integrator. That's a technical term. The input to f And then now we get h squared error, right? Which normally would be a problem because we've got this happy guy here. He's got hair. And he's happy because there's cubic error, right? The whole point of not using forward Euler is that it's only quadratic in this term, right? But lucky for us, there's an h sitting in front of this, so we can get away with a worse approximation of f of yk plus 1 than the outer expression. That's the sneaky trick. So at the end of the day, oh no, I kind of got in the way of my equalities here. What I get is yk plus 1 is equal to yk plus h over 2. And now I've got f of yk plus hf of yk plus f of yk, like that, plus, and it's still h cubed. And notice if I slice this out, I get a locally cubic, globally quadratic accurate integrator. And now it's completely explicit, right? On the right-hand side here, I don't have any yk plus 1s. Isn't that cool? This is a sneaky trick. So what did I give up? For one, this integrator, I mean, I did, like the error changed. Like remember, I did incorporate a new term into my error. And in fact, you can show that this will make this method not unconditionally stable. Like another is a stability condition. The other thing is that notice I have to evaluate f twice now. Yeah. Yeah. Now, if you go into more fancy versions of this, there are all kinds of methods out there. There are things called like predictor corrector schemes, which try to like extrapolate forward, see if it agrees, and then extrapolate backward, and like ping pong until they agree, that kind of stuff. But we're not going to talk about that here. Okay. So in essence, what have we done? We've derived trapezoid method, and moreover, we have derived another integrator called Hoynes method, I believe. My German's not so good. We've established this already. Where you essentially introduce an approximation of the implicit part, then Taylor series your way out, and then note it, and then like essentially the sneaky thing is that you actually didn't affect the accuracy when you did that. Okay? I love this stuff. This is so cool. Now, this trick extends. We are not going to derive it here because we're low on time. But essentially, oh, by the way, you can show that the stability of this thing is the same as the stability of forward Euler. They agree. Now, one thing you might notice is like, so what is my trade-off? Like the stability is the same as forward Euler. The accuracy is higher, but each step now takes 2 evaluations of f instead of 1. Right, this is this annoying Pareto frontier. There's like all different ways to compare these integrators, and sadly, there's not one that everybody loves. Yeah. How expensive are evaluations of f? It depends strongly on the problem you're solving. In some corners of physics, it can actually be quite expensive. So think about planetary simulation, where I have like n planets that are all swirling around, and the gravitational force is between every pair, so it's quadratic time. That's the sort of typical example of really slow thing. In fact, GPU demos often show like giant planetary simulations because it's kind of cool. It's also the motivation behind the fast multipole algorithm, if that's your bag, which is not a thing we will cover in this class. Was voted one of the top 10 algorithms of the 20th century, according to a magazine article I read. Yeah. I also had a really weird interaction with the guy who invented fast multipole, but the camera's on. Okay, so in any event, the textbook works out the stability of Hoynes method, but like spoiler alert, it's just the same as forward Euler. Ta-da. Okay, so more generically, there's an entire class of numerical integrators. These are called Runge-Kutta, Runge-Kutta, I have no idea. Every time I give these lectures, I mean to look it up, and then I don't. But essentially what they do is they take each of the quadrature rules we talked about 2 lectures ago, like trapezoid, midpoint, Simpson's rule, right? Each one of those things, like what would Simpson's rule does? It like has 2 values of the endpoints and 1 in the middle. And so now, what do I have to do? Well, I have the middle guy and the third term. And now both of those ones, I'm going to put Taylor series inside and then use basically an identical argument to what we did on the board. As you can imagine, these get ugly to write down. It's basically just like this recursive procedure. But each one of those gives you a different RK integrator. So like essentially like you have, I think this is RK2, I guess. So there's like RK1, 2, 3, and 4. The most famous integrator in this class, maybe this is RK3, I don't think that. Yeah, I guess so. is RK4. This comes from Simpson's rule, which is why you see 4 terms there. And essentially, it's just the same procedure. And you can kind of, in fact, if you go on Wikipedia, they have this wild diagram where they try to take this picture. Oops, where did it go? Remember I drew that plot and there was like extrapolations? I guess I erased it. The picture I was drawing, and they try to like draw the RK version of this. It's worth a look just to be like, wow, this is really bad scientific illustration. But like really you can kind of view, like for instance, K1 is the slope at the first time step. K2 is kind of like the slope at time 1/2. K3 here, well, it's a little bit tricky because now you go back to the first time step and then use the slope at time 1/2, right? So like this is kind of like using a better integrator because this is the midpoint, right? So you can kind of like squint your way through this thing, and Wikipedia has this wild diagram where they try to make you, they try to justify each one of these things. But the reality is that really it's just this trick applied to different quadrature formulas. Okay. RK4, I think, is generally regarded to be like the good default explicit integrator. Like it's got 4th order accuracy, which is good, and it's explicit, so it's pretty easy to implement. And so like I think this is usually like kind of the default option in a lot of software. Okay. So that concludes our discussion of like the basics of numerical integration. If you had to stop and like, you know, like you went to bar trivia and like people, and they had a special category on numerical integrators, those would be the ones that they'd ask about. But of course, this is the tip of the iceberg for like all kinds of cool stuff you can do in numerical methods. In this lecture, we're going to attempt to cover 2 more. We may only get to 1. We will see. Okay, so the first one is going to kind of address, I think, what's really a contradiction from the last lecture in this one, which is that we spent all of this time analyzing behavior of like a million different integrators, right? Like we've just analyzed the bejesus out of all these different integrators, and all of them we've used the same analysis technique, which is we plugged in the model equation, and then we asked like, you know, was it stable on this thing? And was it accurate, by the way? You could compare, because the model equation, we know the solution to it. We know the steps of our integrators. We can just see if they look similar or not. But like in a sense, I mean, the question you guys should all ask is like, well, wait a second. Like this is totally dumb, right? Because we know the solution to that equation. Like why wouldn't we build numerical integrators that have the solution to that built in? So in other words, like if the ODE that I happen to try to solve is linear, then my integrator is perfect. Right? Like we don't have that property right now. Even for linear ODE, our integrators are approximation. Notice that that's different than like other parts of this class. For example, in Newton's method, what did we do in Newton's method? We took a quadratic approximation, we minimized. And notice that like if my function happened to be quadratic, Newton, how many steps would Newton take to converge? 1. That's quick. That's right. And so like it would be interesting to have an integrator with a similar property. And not only interesting, by the way, it's practical, because it turns out that, like, unsurprisingly, a lot of physical systems and things that we solve with ODE are nearly linear. Like, the effects are not that, the higher order effects are just not that strong. Right? Anyway, I get all excited because I think this is my favorite class of integrators. Like, everybody has a favorite. This is mine. You will too. So the basic idea here is that we're going to derive an integrator that says, well, I know the solution to this, so I'm going to bake it in and then just look at the difference between the linearized version of my problem and the true solution and try to just approximate that piece. And that leads to a different class of integrators called exponentiation, or exponential integrators. Okay? So as a bit of a reminder, of course, once again, there's our solution to the linear ODE. And now, let's do a little bit of mathematical gymnastics. Okay? I think this is not called integrating factors. What is this trick called? Yeah, go back to your laptop. We were just doing this in my office a couple weeks ago. But yeah, I know. So the sliding window is too long. With the heat equation, you can do. Shoot. Yeah, that's stuff. Jeez. You guys kill me. Okay. Well, there's a trick in ODE which has a name. Variation of parameters, that's the name. And it translates to a nice integrator for equations. Okay? So here's going to be the basic equation that we're going to try and solve. This looks like y prime equals ay plus g of y. Okay? Notice that, like, essentially what I've done is I've put an ansatz on the form of our generic f of y that we had before. Right? So I'm saying it's the linear thing plus something else. And I can always get this, by the way, right? Like I could take Taylor series of f and just have this be the first term. Okay. You look confused. Oh, Ansatz, German word for assumption that math people like to use to sound fancy. Okay. I don't know. You know, as usual, Americans like to pick up words from other language and then abuse them and then incorporate them into our everyday usage. Fredo Durand gives me a very hard time about like American, like Americanisms that are like somehow French but like completely wrong. But I digress. Okay, so right, so the ODE that we want to solve is y prime equals ay plus g of y. And we want the property that if g equals 0, then we solve the ODE exactly with our time stepper. So how are we going to solve this? Any ideas? I wouldn't either. Like this actually like totally subtle how to derive this thing. This I think has its history. You remember I mentioned that like if you took ODE 100 years ago, you would just spend like a bunch of time learning weird tricks to solve them by hand. And I think this kind of falls into that category, but it does translate to a nice algorithm. Okay? So, right, so of course, one thing that I can do is isolate g, because that's sort of the part of the problem that we don't know anything about. So this is the same as y prime minus ay is equal to g of y, like that. Okay? And now, here's what I'm going to do. I'm going to multiply both sides by e to the minus at. Okay? So, what is this? So this is e to the minus at times y prime minus ay is equal to e to the minus at times g of y. Hopefully we all agree that this is true. What should I do here? Are you guys good at eyeballing calculus tricks? What is the derivative of e to the at with respect to t? It's like e to the at again times a, right? And notice that I kind of have like a y prime and an ay. So in fact, this expression is equal to d over dt of the product e to the minus at times y of t. You guys see that? Because notice that like, you know, remember the product rule? So we have a y prime times e to the minus at, right? That's like the first guy. Right? And the second one, I don't differentiate the y, but I do differentiate this guy, so I end up with a factor of a. Cool? This is sneaky. These calculus guys, they think everything. Okay. So I have d over dt of this thing is equal to this guy over here. So we've only failed to use one magic trick so far, which is the following. We can integrate this thing with respect to dt, right? So what I'm going to do is I'm going to integrate both sides dt, like that. And what do I get? Well, I'm going to integrate it from 0 to t in particular, like that. So first of all, what is the left-hand side integrated from 0 to t? Luckily for us, there's a famous fact from mathematics that we can use. Fundamental theorem of calculus, that's right. So in particular, we've got e to the minus at y of t minus, what is e to the 0? Identity, that's right, times y of 0 is going to equal the integral from 0 to t of e to the minus at g of y. And remember that y is really a function of t, like that. Cool? All right, we're almost done, I promise. I'm like, if I really, really slowball this one, then I can throw off the math that I don't want to do today till the next lecture, but that wouldn't be good. Okay, so I'm now going to multiply both sides by e to the at, okay? And what do I get? I get y of t is equal to e to the at y of 0 plus the integral from 0 to t. Okay, so now I'm going to change the integrand here to a tau, okay? Just because I can. So we've got e to the a t minus tau, okay, times g. By the way, I really should have done that here because you see there's two t's here. Like, yeah, my high school calculus teacher would do a -1 on that one. G of y of tau d tau. Okay. Have you ever seen this formula before? I think this is a cute formula. This is called variation of parameters. And notice what it's doing. When g is equal to 0, notice that this is just the solution of the ODE. Right? So essentially this is saying like this is the sort of term that's compensating for the nonlinear part. Well, remember our strategy, like in fact it's all the way at the top of the board here for like deriving new integrators. Like we come up with some clever formula. This guy so far is an equality. And now like it's like, you know, y of t is equal to something computable plus an integral. What are we going to do? Do a quadrature rule. We do a quadrature rule here, and for every different quadrature rule we put here, we get a different numerical integrator for our ODE. But notice that unlike the previous ones, this one is exactly correct for the linear ODE because it's just quadrature on 0. Isn't that cool? This is such a sneaky trick. I have an old research paper that uses this trick to solve Hamiltonian Monte Carlo problems, which is a good example of the kind of integrator that needs this trick. So that was actually, I think, one of my proudest research papers I've ever written, even though it's like a footnote, because it's like the only time this will ever happen in my professor career where I sat in someone else's talk on HMC and just raised my hand like, oh, you should use this thing. And then it worked. Okay. Right, so, so in particular, so this was the integral from 0 to t. We can, if we want to derive a time step, we should change this formula ever so slightly to say like, well, this is really yk plus 1 is equal to e to the a time step, right, h, times yk, plus the integral from tk to tk plus 1 of e to the a, maybe a little careful with this change of variables, tk, plus h minus tau g of y of tau d tau. Okay, so all I did here was just shift the previous formula by tk. Okay, so there are all kinds of different things you can do to derive integrators based on this formula, and all of them have the nice property that they work perfectly for linear systems. One of the easiest ones that we can do is just use forward Euler. So in particular, we can say like the world's worst approximation of g of y of tau is just g evaluated at y of tk, right? Like this is like basically, yeah, the forward Euler approximation. So in that case, what do I get? Well then, essentially, I think notice at that point, this guy moves outside of the integral. So what I'm left with is the integral of e to the stuff, d tau. I don't think it's worth working through this integral because it's not going to be meaningful for you guys anyway. It's just another linear algebra calculation. But the final formula that you're going to get is the one on the screen here. This is called the first order exponential integrator. It's first order because this is a first order approximation of this integral because of this approximation here. And essentially the point here, I mean, if you look at this expression here, I mean, it has some nice properties and some really horrible properties. The nice property is that it works really well for linear ODE, and when g is small, it also works really well, right? Because it's essentially just a small compensation factor. It's also like the stability, by the way, is really interesting and hard to analyze. We will not be doing that here. If you think about it, like our argument for stability, it was to evaluate stability on the model ODE. From that, then this is of course unconditionally stable, but that's because like that's not really the right stability rule. I mean, you should be looking at the dependence on g. But the good news is that oftentimes what you can do is you'll have physical systems that are highly oscillatory, but in a linear fashion. So like I'll have like things that are basically really, really springy, and then I'll just have some additional like kind of compensation terms. And so the good news is that sometimes you can kind of use A to take care of the parts that are making this really ill-conditioned. And then what you're left with is some like low frequency behavior in G. And that's when these kinds of integrators are usually useful. That make sense? What about the computational expense? What's that? There's an A inverse, so like at the very, and so it's like at least as bad as backward Euler. Any other thoughts? Yeah, the matrix exponential, if I want to actually compute it, I need to compute all the eigenvalues of A. This is an expensive operation. Incidentally, there's a really fun, I think fun, a document out there on the internet. It's called like 20 Bad Ways to Compute a Matrix Exponential. Very famous. There's actually a whole series of these really famous numerical analysis papers that are like 20 bad ways to invert a matrix. But in any event, they go through all kinds of bad approximations of this and show that they're like problematic numerically. Yeah, so that's really where this falls apart. So it's like okay when A is small, like maybe in physical system where it's like 3 by 3 or something, but for really big problems it becomes really hard to compute. Oh sorry, yeah. There are specialized algorithms out there for matrix exponential, but I think the reality is most of them just implement the eigenvalue stuff. Yeah, that's a good point. So like for instance, maybe A here is negative definite, which is often the case for diffusive PDE, like heat equation. Then one thing I might do is just compute the top eigenvectors because of course A times H is basically decaying the eigenvalues that are biggest the fastest, right? That sentence was hard to parse, but I think it was correct, right? Like e to the minus at goes to 0 really fast if A is big. And indeed, that is another approximation people do. If you want to be careful with that, then you have to be careful, like, okay, well now you don't have an exponential integrator anymore, right? You've introduced basically an approximation of these e to the AH terms, and then you got to do your accuracy analysis again. An even dumber approximation, by the way, is like, we have the Taylor series for e to the AT, right? So you could just put that here, and you'll very easily get an order H approximation, and what you'll find is that you're back at a forward Euler integrator again. There's like, again, there's like some really annoying balance between accuracy, stability, efficiency. This is very far in the low efficiency regime, which is what's buying you low efficiency and potentially high stability. Yeah. Okay. So that concludes our discussion of first order integration. There's only one problem. The differential equation that everybody cares about is f equals ma. And we showed how to reduce f equals ma to this case, but that doesn't mean that our integrator is necessarily the best one. And so essentially, the last topic that I wanted to cover in numerical integration, I'm like looking at the clock, we're 25 minutes, I think I can do it. This is famous last words. It would be nice to do it so that the next time we'd be freed up for a new topic. But the point here is that like that is a way to solve f equals ma, but it doesn't have to be the way to do it. I only have 3 pages of integrals to go through, so no problem. Okay, so in particular, let's say that I want to solve a higher order ODE, right? What we're going to find is that we can use different, so remember that we can always do the reduction to first order using the trick that's on the screen here. Hopefully this looks familiar. Here's going to be the kind of sneaky thing that we're going to do, which is just wild. We're going to argue that like the thing that we want to be a high quality approximation is y, the letter y, right? It's not v or a. Like those are just side variables I introduced, right? And what we're going to find, like so far, the analysis that we've done has shared the same order accuracy for every element of our vector. We're going to, in effect, derive integrators where the first element, like y, is going to be really highly accurate. The second one, like v, will be medium accurate. And maybe the third one, like a, is going to be not accurate at all. And that's going to be okay, because the thing we care about is the position, it's the y's, right? So like notice that our theory so far can't really account for that, because we only have one giant variable y and one derivative, okay? So like there are a lot of clues for why such a thing, such a thing might be possible. So like a different way to do it, let's say that I even was in the first order ODE, and I wanted to approximate like this. I'm going to write the same expression we've in effect written about 5 billion times here, right? So this is h times y prime of tk plus h squared over 2 y double prime tk, like that, plus order h cubed. One thing you might have noticed that like went by a little bit fast in our derivation of the trapezoidal integrator is that like there's a factor of h here, right? Which means that if we only approximate this guy to first order, then we get a second order approximation of y. You see that? Because it's multiplied by an h. Similarly, if I approximate this guy even worse, luckily for us, there's an h squared here. So it can do even worse. Right? So that's basically our evidence that like maybe it actually makes sense for a second order ODE to not collapse it and forget about that second order term, but actually to keep it there and approximate the different pieces using different formulas. Like do forward Euler on V and midpoint for Y. Oh no, I gave it away. Okay, so let's do that. By the way, in this lecture, we're only going to worry about second order ODE because who cares about higher order ODE? Not me. I say that, but like, because if second order ODE is like all of physics, beyond that, like, you know. But all of these tricks do apply to the higher order stuff. I'm sure there's like some very complicated stock market model out there somewhere that has a bunch of higher order derivatives. But in particular, we are now going to switch our attention to a new ODE, f of t, y, y prime. Right? So now we essentially added a new input to f. And the reason we're going to do that is we're going to approximate y prime less accurately than y. Okay? Everybody understand the motivation here? Okay. And in particular, we're going to derive an entire class of integrators at a time. These are called Newmark integrators. They're apparently named after a guy named Newmark. And this is like one of these magic formulas where like there are going to be a few constants in there, and depending what constants you choose, like you can make it implicit or explicit. You can change the accuracy. It's like an entire class of integrators all in one shot. The only problem is that it's really ugly. So get psyched. I'm tempted to put the screen away here because like this really is a lot of calculation. I'm going to try and do a planning problem, so I might write a little smaller on the board than we normally do. If you can't read anything, you should tell me. Okay? That's my. Unfortunately, I think for students, like a disclaimer like that is usually code word for like, okay, get out my iPhone and like start, you know, Angry Birds. But like try to stick with me and we'll see if we can do this together. Okay, so Newmark integration, like essentially we're going to use this change of variables on the screen. Like we are going to have variables y, v, and a, but we're going to come up with different integrators for each one and we're going to see how they play together. Okay? So in particular, we're going to start by our kind of favorite usual trick. So for example, what is vk plus 1 is equal to vk plus the integral from tk to tk plus 1 of the acceleration, like that. Okay. Start out easy. And we're just going to kind of like memory bank this formula for a while, because we're going to come back to this guy and do like kind of bad quadrature on this expression. Okay. But now we're going to do kind of a weird thing. I know, this is shocking, right? In particular, let's write the same formula for yk plus 1. So this is equal to yk plus the integral from tk to tk plus 1 of v of t dt, like that. But now, notice that we have something at our disposal that we didn't have before, which is a derivative of v, right? We have a. Right? So let's say that we wanted to write this integral in terms of a and not v. How could I do it? Integrate it by what? By parts. Right? So in particular, like if I want to kind of engineer an expression with the derivative of v in here, remember how I can do that? I could kind of differentiate one thing and integrate another. So let's say that I write this in kind of goofy way. This is equal to the integral of 1 times v. So remember how integration by parts works? I can differentiate the v and integrate the 1. So let's write our integration by parts formula. I'm going to get yk, and now remember how this works. You have a boundary term, which is the integrals multiplied by each other. So this is like t times v of t, integrated, evaluated at tk and tk plus 1, like that, minus the integral from tk to tk plus 1 of t times a of t. So this is integration by parts. It's kind of, for some reason, this is like an uncomfortable formula to me. Like, it looks weird, but I don't know why. It is correct, I think. Yeah. By the way, can you guys read this? I'm writing a little smaller. Yeah. And whenever there's a squiggle underneath the t, you can safely assume it's a k plus 1 here. I should probably write it as like bar or something, but whatever. Okay. So there's our integration by parts formula. And now we're going to do something kind of funny, I know, surprising, which is we can actually write this in yet another way. which is because tk plus 1 is the same as tk plus h, right? So in particular, we're going to write a really funny expression and then justify it. So this is equal to yk plus hvk. So notice that that is like the second thing here, but we forgot the tk part of that term. Plus tk plus 1 vk plus 1. Okay. Minus tk plus 1 vk minus the integral tk to tk plus 1 ta of t dt. Okay, so let's decompress this a little bit. I know it's ugly. I'm sorry. Some proofs are just not nice. This is one of these. Okay, so here's what we did. We have tv of t, right? Like notice that like essentially all I did was expand that term into these three guys, right? But in particular, what is tv of t? Well, it's vk plus 1 times tk plus h, right? Which is tk plus 1, right? So in particular, there it is. Now we have minus, what do we have? tk v of tk. So we've got, I could have written tk times vk here, but instead I put a tk plus 1, and I'm going to add this hvk to compensate. Everybody with me? I know it's annoying. I'm not sorry. Okay. So why on earth would I do that? So what is this guy? Well, I can factor a tk plus 1 out of this thing, right? So this is equal to tk plus 1 times vk plus 1 minus vk. Uh-oh. What should I do? I have a difference in v's. Use the fundamental theorem of calculus, right? This thing is equal to tk plus 1 times the integral from tk to tk plus 1 of a of t dt. Right? Because a is the acceleration, and this is the change in velocity. Yeah? Okay. So if I put that into our expression, oh man, I wanted this to fit. Will you guys be offended if I erase this bottom line here? I want you to all count to 5, think, digest this line. We're good. I think we only have one student that's actually taking notes. Okay. So I'm going to erase it, and then I'm going to write the final conclusion. Ugh. Which is, this is equal to yk plus h times vk plus the integral from tk to tk plus 1 of, so notice we've got a tk plus 1 minus t here, like that, times a of t dt. Okay? So isn't that cute? This is like actually a pretty nice little formula. So at the end of the day, essentially this gives us a formula for yk plus 1 in terms of yk, vk, and some integral involving a. Cool? And that's kind of good because like, at the end of the day, remember like our trick for deriving quadrature rules? Like we took integrals and we approximated them. And in this case, the thing we're going to want to integrate is going to be the a term because we now have like y's and v's around, and both of those are things we're going to maintain. So that's our trick, is we're kind of pushing the integral into the highest order derivative. Okay. So, whew. So there's our sort of fundamental little formula here for Newmark integration. If you're wondering, we're only like about a third of the way through. So now we're going to derive a whole class of integrators by doing all kinds of tricks that involve massaging this integral into different forms. Okay, so I'm going to do a thing that I always used to hate when my math professors did, which is like that. We're going to continue in the space we have left. Okay, so in particular, here's what we're going to do. Take any tau, which is going to be between the two time steps. So between tk and tk plus 1, like that. Okay? Well, here's what we're going to do. We're going to write formulas. Like essentially now we're going to do something that looks an awful lot like what our old derivations of integrators. We're going to write a formula for a, the two size of the time step in terms of a tau, right, just by using a Taylor series. So in particular, we have AK is equal to A of tau plus A prime of tau times TK minus tau plus, and now it would be the order of this guy squared, which is actually just h squared, if you think about it, right? Because TK minus tau is like somewhere between, it's like let's let h, right? Because tau is in this range. Everybody with me so far? Okay, similarly, we can write AK plus 1. Well, this thing is also equal to A of tau plus A prime of tau now times TK plus 1 minus tau plus order h squared. Okay, so these are just the identical formula evaluated at 2 different places. So this is Taylor series. So now I'm going to do kind of a funny thing. I keep saying that. This is one of these derivations that I'm like really not sure the history, but like I looked through a few different sources and they all follow more or less the same outline. Okay, so now we're going to take any gamma. And by the way, like the taus and the gammas, and there's going to be one more constant, which is beta, are going to be like the parameters of our integrator later. Okay, so we're going to take any gamma, and actually gamma can be any real number, it turns out. And now what we're going to do is we're going to take this first guy and multiply it by 1 minus gamma, and the second guy and multiply it by gamma. We're going to add the two together. So we're going to take like a weighted average of these two expressions. And the reason is that like notice that both of them have A of tau there, right? So like somehow that part is going to persist, and then we're going to get weighted averages of the other two terms. Does that make sense? Okay, so in particular, oh man, I'm not looking forward to this. Okay, so we've got, I keep saying that. I am looking forward to it, because this is exciting, and you're learning numerical integrators, and those are beautiful. You should be excited too, because I'm excited. So A of tau is going to be equal to, oh boy. Okay, we've got a 1 minus gamma times AK, right? So that's going to be like this guy, remember, is multiplied by 1 minus gamma, and then plus gamma times AK plus 1, right? We've got, and now let's gather all the things that involve A prime of tau. Okay? So let's see. So this is going to be A prime of tau. Then we've got gamma minus 1 times TK minus tau. Tau. Right, so that's like this guy. But remember now I've moved to the other side of the equation, which is why the sign's flipped. Okay? And we've got a gamma times gamma times TK plus 1 minus tau. All of that. Okay. Now we have an order h squared. Everybody see how we got from these two expressions to this guy. This is a weighted average of these two formulas. Okay. So we can simplify this guy a little bit. In particular, like this thing in these parentheses here, we can like kind of multiply out and then gather like terms, right? Our usual algebra. And what we're going to get, where is it? Oh, there it is. Okay. At the end of the day, if you multiply this out, you're going to get gamma times TK, gamma times TK plus 1. We know that TK plus 1 is just equal to TK plus H, right? So there's like some cancellation that we're going to be able to do. So I'm going to write an equivalent expression here, which is to say that this is equal to 1 minus, like I'm just copying stuff first. So this is equal to 1 minus gamma times AK plus gamma times AK plus 1 plus A prime of tau. And essentially just after the simplification, you're going to end up with tau minus H gamma minus TK. And that's it. And this is just making use of the fact that TK plus 1 is equal to TK plus H. That's all. Okay. Have I lost you all yet? Because I can keep trying. Okay. So we're almost to the end of my second page of notes here. Okay. So in particular, just in case this is going to get weird, a little absurd. I'm going to take this expression for a of tau. And remember what I'm trying to do. If I go all the way back to our original thing, I'd like to be able to integrate the a's to get the v's. So now I'm going to integrate this expression from tau equals tk to tk plus 1. So in particular, I'm going to get that vk plus 1 is equal to vk plus the integral from tk to tk plus 1 of a of tau d tau. Okay? And now I'm going to plug in this expression here. And what's going to end up happening? Well, the good news is it kind of doesn't matter. Like we're only going to really need the lower order terms here. So maybe I'll just go ahead and give you the result. Essentially, what's going to be kind of boring here, notice that like these two things, they have no tau, right? So when I take the multiple here, it's just h times that. Do you guys see that? The integral of this is just h times this expression. Okay, so we're going to do those two terms first. So we've got that this is equal to vk plus, now we've got a 1 minus gamma times h times ak, like that. Okay? Then we've got plus gamma times h times ak plus 1. Okay? And now here's a really horrible thing that we can do. We're going to integrate this d tau over a little tiny time interval, right? So if we kind of squint at this thing, one thing we can argue is that this is roughly order h squared. Let's see if we believe that or not. So in particular, here's how to think about it. Look at this expression, right? So first of all, there's an h here, so this is already order h, right? And here we have tau minus tk. And remember that tau is somewhere between tk and tk plus 1. So this whole thing is also order h. And what happens if I integrate an h? I get an h squared. Ta-da! Yay, I managed to fit all this stuff onto one board. I'm very happy with myself. Okay, so now, in the 5 minutes we have remaining, we will do just this much more math. We're almost there. Okay, so, sorry, I'm going to swap the two boards. Ah! We're going to keep going because it would really be a shame to get like 82% of the way through this and then have to stop. So we'll see if we can avoid that situation. So in particular, now we're going to have a new constant, which we're going to call beta, and it can also be any real number. Okay? And now, if we go back to our formula that we derived up here, remember that like at the end of the day, we have this funny integral of like t against a of t. This is the thing we're going to try and approximate. Okay, so in particular, what can we do? Well, we can use exactly the same trick that we did here. And we can plug in this expression for a of tau. Right? So what are we going to get? We're going to do the following. We're going to say this is the integral tk to tk. By the way, all of these steps are written in the textbook. This is copied verbatim, so like, you know, later on you can go back and read it slowly. We have tk plus 1 minus t a of t dt, right? That's the expression that we're trying to approximate. And what we're going to do is we're going to substitute in this expression for a of tau up there. Notice that this thing is basically some polynomial in tau plus order h squared, right? Order h, rather. That's what we argued to get this expression. So by an identical argument, I am going to skip a step. I'm sorry. I know I get frustrated too. But like essentially by an identical argument to how we got this vk here, we can get a similar expression for this integral by just plugging in that formula for a of tau above, and then like kind of grinding through it. And what we're going to get is that this is 1/2 times 1 minus beta h squared ak plus 1/2 beta h squared ak plus 1 plus order h squared. I think that's actually a cubed, sorry. And so the basic point here, notice that you have these h squareds. That kind of makes sense because this whole thing is multiplied by a t here, so you kind of expect something like that. Okay. So we're almost done. Why did we have this integral? It was one term in our expression for yk plus 1. So now we're going to substitute that in for this integral here, and we're going to get that yk plus 1 is equal to yk plus, we have an hvk, plus this expression here, which is going to be, actually this is squared, sorry. Sorry, I'm thinking. Yeah, plus 1/2 minus beta times h squared ak plus beta h squared ak plus 1 plus order h squared. Okay, and again, all of that I've done here, I know this looks really complicated. I want to keep stepping back and reminding you that like this is a bunch of annoying steps, but it's really not hard. Like I've gone back to this expression for a of tau, but now every time there was a gamma, I've used a beta instead. Like whatever, that's fine. And now I've done exactly the same integral, but with this factor here, and that's the only difference. That's this expression. Are you guys willing to believe me because we're low on time? We're so close to being done. Okay. Again, it's identical derivation to the one that we did carefully. Okay. The good news for us is we're done. So, in particular, here's what Newmark integrators do. They do the following. Slash out this order h squared, slash out that order h squared in our formula for vk plus 1. Not to worry, this is going to be on the screen in a second. And what is ak? Well, it's just equal to f of t times tk, yk, vk, right? But like, if we step back 100 feet, like these formulas are ugly, but they actually define an integrator. Do you see that? Like all I have are the yks plus 1s, the vk plus 1s, and we don't really need a because it's just defined in terms of these guys, right? And that's exactly what these formulas give us, right? This gives us yk plus 1 in terms of yk and ak plus 1, which is really just like some function of yk and vk. This guy gives me vk plus 1 in terms of vk and ak plus 1. So we're done. We actually have some integrators. So let's look at a cleaned up version that isn't my terrible handwriting. Right. Here it is. So this is the formula that we derived. Both, the first two expressions are really plus order h squared. Right? That's what we showed on the screen. And this is an entire class of numerical integrators. This is called the Newmark class of integrators. I see your hand. I'm going to finish this out. And essentially for every choice, remember like how did I define this formula? It was just like take an arbitrary gamma and an arbitrary beta. For each choice of gamma and beta, I actually get a different second order numerical integrator. Right? So for example, why might I want to do that? So let's say that I choose, so like the right-hand sides of these, notice I have ak plus 1s in two expressions. So what happens if I put in beta and gamma equals to 0? Well, then my integrator becomes an explicit integrator. I killed all the implicit part. You see that? On the other hand, we can see a lot of other special cases. We're going to go through them really fast in the next few slides, just to show that like different choices of gamma and beta actually give us different integrators with different properties, which is super cool. Sorry, Harry. Oh. Yeah, I believe that's right. So I think what ended up happening is if you, for particular choices of these constants, these orders end up being higher. I'd have to go back and double check. Yeah, that's a good point. We went through this whole motivation, and then we kind of forgot it at the end. but yeah, that's what the. And in fact, it'll be on the slide here. I'll show you some examples, and then we can think through together why it's different. So. Here's the simplest choice. By the way, when you start plugging in constants, these integrators look a heck of a lot more simple. So if I put in beta equals gamma equals 0, I get the following. Notice that this is like a wildly simple integrator. What is it saying? It's just saying that like this is the second order Taylor series for y and the first order Taylor series for v, and it's a linearly accurate thing. and it's an explicit integrator. If I choose beta equals 1/2 and gamma equals 1, then I get this other thing, which kind of, if you look at it, like what's kind of going on here is there's like backward Euler happening for velocity and midpoint for position. And this is actually an example. Unfortunately, the accuracy here is still first order. Right? So our bound so far is not so helpful. You guys, by the way, do you see what's going on? This is just like combining two integrators. And this is why I think Newmark did the constant he did, because then it like allows you to kind of munge around these formulas and get different stuff. Here's another good choice, which is beta equals 1/4 and gamma equals 1/2. And then you get, it's just the trapezoid rule. And notice this is our first example to go to Harry's question. We already know trapezoid integration is second order accurate. So this is second order accurate in both. And now we can do central differencing, which is yet another one of these things. Which is kind of used, now you can kind of see like the center difference approximation for A. So do you see the kind of the magic trick that happened with these integrators? We prove one generic formula, and then it turns out that depending on different choices of the constants, you can just recover a lot of examples of well-known integrators. And they're integrating the v and the y differently. Now to go to Harry's question, which honestly we didn't answer here, but I should have. For one, this is just a general thing, but actually you can prove that exactly when gamma is equal to 1/2, you get a second order accuracy. Let's see if we can eyeball that on the writing here. So the gamma happens here. So I guess when gamma up here, right? So when the gamma is equal to 1/2, what is happening? I don't know offhand. I don't know. We'll have to think about it. Like my best guess is if you go through this proof and you substitute in gamma equals 1/2 here, then probably this 2 becomes a 3. But I'd have to think about why. But like which sort of makes sense because this is midpoint. But I don't know offhand. It's a very good question. I didn't really think about it. I should also revise the book ever so slightly to just answer it, because I'm sure that it's like just a small derivation, perturbation of what we've done. You can actually prove all kinds of other fun stuff. Like we're not going to do this in this class, like for God's sake, enough already. But you can show that this thing is unconditionally stable so long as 4 beta is bigger than 2 gamma is bigger than 1. And otherwise, the stability radius is some function, unsurprisingly, of beta and gamma. Okay, so with that, we're over time, so I'll call it for the day. In our next lecture, we're going to begin by proving or deriving one final numerical integrator. I can't help it. I'm sorry, guys. I love this stuff. I'm an addict. Which is going to be the staggered grid or leapfrog integrator. This is roughly the one that you're analyzing on your homework. And this is a different way of doing velocity and acceleration and position in like different calculations. It's actually much simpler to derive, which is good. And it's got a really interesting property, which is reversibility. Like certain ordinary differential equations, if you like flip the sign, time goes backward. But these integrators don't have the property that you'll get the same solution. This one does. So we're gonna prove that property. After that, we have a quick choose your own adventure. We can do one of two things. The goal that I had for this class, but it doesn't matter, was to derive what we call the adjoint method for differential equations, which gives you a way to differentiate the solution of an equation in its parameters. So think about like differentiating, the position at time t of a pendulum based on the weight of the pendulum. And the reason to go through that is that this is useful in a method called neural ODE, which is very popular in machine learning. Or we can have some exam review. What do we vote? Do we want to do neural ODE? We have 3. Exam review. It's okay. We're too shy to vote. Okay. And Chris is like in cyberspace somewhere. Okay. So with that, we will see you guys on Tuesday. Have a fantastic weekend. Enjoy your homework.